next speaker is from Acronix. Our speaker today from Acronix is Mike Fitton, who is Senior Director of Strategy and Planning. Mike has more than 25 years of experience in signal processing, system architecture, algorithm development, and semiconductors across wireless operators and network infrastructure, and more recently in machine learning. And Mike's going to be talking about the fourth FPGA wave. Mike, looks like your screen is shared. You can go ahead.
Well, thanks everybody, and thanks for attending today, and thanks to Rajan for the previous contribution. So today what we're going to do is we're going to follow up from what we talked about last year at Linley. Last year we spoke about the three waves of FPGA, going from the mid-80s when Altera and Xilinx kind of pioneered FPGAs there with programmable I/O and predominantly using glue logic. Then going into a phase in the 90s when there was much more connectivity being supported, so it's much more kind of networking and switching and other applications like that. And then what we focused on last time round particularly was looking at the third wave here, which is much more in kind of data acceleration. So this is where you've got a CPU, for example, and you're offloading the functionality there, where you're doing some data acceleration. So that could be, for example, machine learning. So the example in Microsoft Azure with Brainwave would be a good example of that. Things like network function virtualization. And then as we start to push to the edge, both edge compute applications and 5G. So this is what we said last year. And now what we want to do is transition to thinking about how FPGAs are being used. As we look going forward, FPGAs are obviously with the news of Xilinx and AMD. FPGAs are very much in the news at the moment. And the interest in FPGAs is really driven by this idea of offloading some of the complexity from the CPU to some kind of reprogrammable engine. So Rajan was just talking about that from a fungible perspective of offloading the networking part. Similarly, with an FPGA, you can support networking applications, but you can do other kinds of workloads as well. So you've got effectively a flexible, reprogrammable workload-specific accelerator in the FPGA. You can tell I work at an FPGA company because the FPGA is huge and all the other parts are small here. So the focus that we want to talk about today is building on top of the three waves that we previously had, is where are we going next? So we see, from an Acronix point of view, we see that the next opportunity that we have is going to the fourth wave of FPGA. And that's where it's much more ubiquitous. It's driven all the way to the edge, which then implies different form factors, different power constraints, different thermal solutions. And so you still have that data acceleration market, but then the edge compute, from what we talked about last year, we see it going even further towards the edge. And I'll talk about some of the drive from that from an overall perspective. That could be applications like Industry 4.0 with smart factories, IoT aggregation devices where you're trying to do some aggregation and some analytics at the edge to reduce the bandwidth that you have. 5G infrastructure is both centralized, but equally from a radio point of view, it needs to be deployed right at the edge and then front hauled in some way back to the DU. And then a final application area here in autonomous driving, you've obviously got a lot of data that's being processed at the edge, and that needs to be processed there. We see this overall as a really exciting opportunity for edge compute. If we look at 90% of the world, the data that has been produced in the world has been produced in the past 2 years. And the vast majority of that data is occurring at the edge. So it's a well-accepted solution to this is, why don't we, rather than bringing all that data to a central processing area and having high bandwidth and congestion, let's move some of the compute resources closer to the edge. And so we've seen, for example, this McKinsey prediction of a $200 billion market value in the next 5 years, driven by a wide variety of different applications that we have going across the bottom here. Now, from a user point of view, one of the benefits here is, if we look at here in the central cloud, here I am in San Francisco at the moment, and where I used to live in London, if I've got the edge servers and everything is going back to a central cloud, that's going to increase the latency that's associated with these things, and it overall is increasing the cost. If we want to drive down that cost, what we can do is push the edge, push the processing much closer to the edge, much closer to where the users are, and it has a number of benefits. You have a lot more feature agility in deploying new features, so it's much more developer friendly. Obviously, the latency, because of the speed of light, the latency is going to be much better. And all of the new developments in 5G are all about trying to reduce that latency. There's no point then in doing all the processing back in a cloud, which is going to add latency back in. As I said earlier, it reduces the infrastructure cost because you can do things in much more of an efficient fashion. We get more bespoke and enhanced security associated with this. And I think at the moment, everybody sitting in their living rooms at the moment, we see a big transformation with this, with the coronavirus, with COVID-19, accelerating that transformation of much more of a kind of distribution of data. And from an Achronix perspective, we expect to see, that's going to drive different deployment models. If you look at 5G infrastructure, something like a Cloud RAN is much more efficient in supporting distributed usage and users in different places, rather than the traditional approach of having macro base stations that are covering a specific region. So if you want to be able to do load balancing of network traffic across different regions, having that kind of flexibility of pushing stuff closer to the edge and putting more intelligence at the edge is going to become super important. So how do we support this overall? Obviously, I'm focusing here on things from an FPGA perspective. Now you can see classically here on the left is the kind of discrete FPGAs. So they have been around for a number of years now. The kind of attributes of these is, as I said earlier, it's a flexible, workload-specific, reprogrammable hardware accelerator. They can be used for lower volumes for kind of custom applications prototyping and things like that. And generally, if we look now, the latest generation of FPGAs from ourselves and Xilinx and Intel have really high-speed interfaces. We're supporting, with our next device out, we're supporting 4 ports of 400 gig Ethernet. The other FPGA vendors have something similar. There's high bandwidth memory, either with HBM2 or GDDR6, giving multiple terabits per second of high bandwidth memory. So like super high performance of the FPGA is giving it applicability in compute acceleration, things like network function virtualization, data center and machine learning, and then lower volume applications like test. But let's jump to the other side. There's a newer product concept called embedded FPGA. And the idea here is really simple. It's the same FPGA fabric, but it's just embedded in a developer's own ASIC or SoC. So there's no reason really why this can't happen, and it hasn't been able to happen in the past, but particularly as we go to more advanced process nodes, you're effectively able to get more FPGA fabric in with a relatively small investment of die area. There's a number of other embedded FPGA vendors as well as Achronix, but we're unique in the market in that we provide both discrete FPGA and embedded FPGA. As you can see here, this is our discrete FPGA product. It's called the Speedster 7T, the 7T denoting it's a TSMC 7nm product. And then we take that exact same fabric and we deploy that in a customer's own ASIC or SoC. So that will be a region of this chip, which is FPGA based. It has all of the same attributes that you would expect in that it's reprogrammable. After you tape out, once your chip comes back, you can just run the FPGA synthesis tools again, download a new image. And so that means that you can have effectively a new personality for this chip by reprogramming the FPGA region. The fabric is identical and the tools are identical. As in the UK, where I'm originally from, we have an expression about eating your own dog food, about consuming what you produce. And that's exactly what we do here. We have the same hardware development here as we do in the discrete standalone device that we're also going to be shipping. Now, how does this work overall? Effectively, you as the ASIC developer, the SoC developer, get to be the FPGA product planning team within your organization. We have here what's looks like what you might call an FPGA compiler. So you can see up here, we're programming in the amount of logic, the number of 6 input lookup tables, the amount and even the size of the memories. You can have maths blocks either optimized for machine learning or classic signal processing applications. And you can even include custom functions. This could be something like a TCAM memory, a packet passing engine. It's a custom function that can be embedded into the fabric. And then what comes out of this is the software synthesis tools. So you will get our ACE design tools, and then in the drop-down menu, the device that you create is now a new device that you see and no one else does. You see that, and that can become a target from your RTL. And then it's integrated as a GDS2 handoff. It's pretty typical of the other embedded FPGA vendors as well. It's a pretty similar approach that there's effectively a floor plan handoff. And then all of the programming designed for test and verification, that's all kind of shipped in a classic approach for a back-end ASIC developer. But then the other view of it is more from an FPGA perspective. Here's an example that we have of a chip. So the black region would be specified by the end customer. So that's then defining the interfaces here, and then what kind of ARM or RISC-V CPU. And then the blue region, the blue FPGA fabric is coming from us, being delivered by Achronix, but that allows you to have a new FPGA image, a new personality being downloaded. So here what we're doing is an application where we've got something that's got sensor fusion, for example, so it could be used in an autonomous driving application, or can be doing deep packet inspection and can do these things at the same time, or have a new image that's downloaded associated with these things. Now, the benefits associated with embedded FPGA with respect to discrete FPGA. So what I want to do is just take a comparison. Imagine for a moment you've got your ASIC here, and your choices are either having a discrete FPGA that's external to that or something that's embedded. And I'll use Achronix as an example, but this is kind of broad benefits that you would see from any embedded FPGA vendor. Now, generally, the cost is less. So FPGAs are, because of the flexibility coming at the cost of increased die area, can be a relatively expensive way of doing things with discrete devices. It's possible to dramatically reduce that down. So how that happens is, first of all, you're removing the package cost. It can be significant for large packages. Then you're removing the FPGA periphery, the SerDes, the controllers, and the interfaces. Excuse me. So you've eliminated the SerDes, interfaces, and the controllers and the periphery. Then of the core itself, you can right size that core. So typically no one ever uses all the resources in an FPGA. Typically you're going to be maybe memory heavy, but not use all the DSP blocks, or vice versa. So if you're including an embedded FPGA region for a specific application, you can right size that, so you shrink down the size of it. And then finally, the business model that is generally associated with embedded FPGA is a license fee and royalty rather than a chip development. And so that's then eliminating the vendor margin dollars that would be coming to Achronix or to Xilinx or to Intel. Similarly, from a power point of view, we get kind of a half to 4x power reduction. That's really because of you can eliminate the interface power, and because of you're right sizing the FPGA fabric, you're therefore also reducing the FPGA static power consumption. One of the big applications we see from an interfacing point of view, so I've seen this particularly in high frequency trading, where you want a really low latency to get into the FPGA application for doing tick to trade arbitrage applications. Having a lower latency is very important to those trading firms. And because of the way the embedded FPGA fabric can be tightly coupled with a surrounding SoC, you can have incredibly lower latency or higher bandwidth, or both. So that's one of the other benefits from particularly an interfacing perspective. And then you've got both flexibility and extended product lifecycle that I'll touch on in a moment. There's a wide variety of applications. We see some things in machine learning, particularly 5G radio is a good application area. We've had recent design wins in autonomous driving, particularly in the sensor fusion application. I talked about networking and high frequency trading as well. So pretty much as many applications as you could think about for a classic FPGA is also similarly applicable from an embedded FPGA concept as we're driving the stuff to the edge that I talked about previously. So from a product lifecycle perspective, where do we see the opportunity here? So a classic FPGA is high on flexibility, but the die size is higher and the power is higher. So how do we modify that overall? If we look from our standalone devices, we're reducing power by hardening functions, particularly having hardened interfaces for GDDR6 and DDR4, DDR5. But then as you go into the realm of embedded FPGA, you can then take your ASIC and with the modest increase in die size and power, you can add a considerable amount of flexibility. The green region here denotes a small amount of embedded FPGA to give a new application area in that space. Another product concept is more what you might call a custom FPGA, which has a larger region of embedded FPGA and might have some ASIC acceleration in that, the smaller black dot here. That obviously would increase the die size again, but it gives you more flexibility. So the key here and what we're doing from an Achronix perspective is enabling our customers to be able to reach different points on that cost reduction continuum. It used to be just the two endpoints of a traditional FPGA and an ASIC. And now you can sit anywhere on this cost reduction continuum, depending on what's your appetite for flexibility and how much cost can you incur. From a product lifecycle perspective, what we're aiming to do is to enable a tape out earlier because of the late changing requirements go into the FPGA region, so you can hit the market earlier. You can drive more product SKUs, more product variants, because you can have a new personality in that embedded FPGA. And then you extend the product life cycle by having new standards, new algorithms, new requirements are absorbed into the FPGA region associated with that. Here we've got a specific application associated with machine learning. So this is where the embedded FPGA region is doing I would say the boring kind of tedious part where you're getting the data ready for processing. So you're doing interface adaptation. Classically, FPGAs have always been great at I/O adaptation for new and emerging protocols. You're aggregating all of that data together. You're doing some sensor fusion applications. So you're extracting the payloads, you're changing the data format, and then you're aggregating it together so you can do a machine learning workload on the combination of all of your sensor data. If this is autonomous driving, there would be LiDAR and there'd be radar and there would be audio and there would be video, and all of those need to be aggregated together. You can do some data pre-processing, and particularly the compression. If you're doing natural language programming and you're only processing the bits where there's non-zero data, you can effectively get a much higher effective processing rate by compressing the data before it goes into this high bandwidth matrix vector maths engine that we've got here. So the FPGA in general here is a great target for doing the kind of sensor fusion and operations associated with that. In addition to that, for the actual data center acceleration itself, specifically in machine learning, from a comparison point of view, CPUs have got the lowest performance out of CPUs, GPUs, ASICs, and FPGAs. Are relatively power inefficient, but you get a ton of flexibility. You can do anything from a software point of view. Putting GPUs on this graph as well, you get an increase in the performance. You get a more power efficient solution, but it's more dedicated hardware, more focused hardware, so the flexibility tends to drop off. ASIC is obviously going to be off the charts in terms of performance and power efficiency, but it's very specific in terms of the application. And then FPGA and embedded FPGA is kind of a trade-off between all of those things, a compromise where you've got higher performance, although not reaching that of ASIC, relatively good power efficiency, and a nice amount of workload flexibility for all of those application areas that I talked about. Now, if we're looking at specific performance, here I list a number of FPGAs from Xilinx and Intel. So this is now our discrete FPGA rather than our embedded FPGA. But this device has been specifically optimized for machine learning applications, and so that's why you can see a high performance of int8 teraops here of 61 teraops of performance with int8 in the multiply accumulate blocks, and then native support for block floating point, which is very amenable to the kind of data that you get in machine learning applications. So that's something where you can see that if you contrast that with some of the NVIDIA performance down here, that's a higher level of performance, but not necessarily as flexible. And then here, from a Xilinx Versal perspective, this is the matrix engine that is being supported with the vector signal processor there. So again, we've done it by optimizing the FPGA fabric rather than doing a heterogeneous multi-core solution that would be integrated in with everything else. These, if you're interested in the device, it's available for order straight away, and that was on a PCIe form factor card that we developed with Bitware Molex, which has got a generation ahead in terms of performance. It's got PCIe Gen 5 on the device. It's got 400 gig Ethernet with up to 100 gig SerDes, and then this innovative new two-dimensional network on a chip, which allows us to be able to move data around very efficiently. In addition, coming with that is we have the tools that you would expect. So the standard FPGA low-level tools of synthesis, but then libraries that sit on top of that for various different engines, and then a design flow that takes it from high-level frameworks, TensorFlow, PyTorch, Caffe2, and takes that through an intermediate representation and into the takes that through an intermediate representation and targets that onto the FPGA fabric at the bottom. So in conclusion then, what we've seen, these three waves that I talked about previously of where FPGA was used in the past, but the ability to now have embedded FPGA as well as standard FPGA means that FPGA can be deployed much closer to the edge, can be integrated as a chiplet or monolithically in with other devices right at the edge of the fabric. And that brings the benefits of FPGA of future-proofing and flexibility, but to a whole new different class of product. From a specific data center acceleration and machine learning optimization, it's possible to get some pretty significant density improvements, performance improvements, just by targeting the memory hierarchy, targeting the data movement, and targeting the data processing associated with that. Be very happy to go into any more details on this in the breakout session, but that was the end of my presentation, and over to you, Bob.
Okay, thanks, Mike. And you can go ahead and turn off screen sharing so everybody can see you. Since you've got strategy in your title, I'm going to hit you with some business related questions here to start off with. In terms of the fourth wave you mentioned up front, you covered quite a broad range of applications. So I'm interested from your perspective in where you're seeing early adoption for embedded FPGAs.
Yeah, so embedded FPGAs, I would say a relatively new concept. Achronix came up with an embedded FPGA back in 2016, and there's other vendors out there as well. We're seeing a number of different verticals. I think earliest adoption occurred in 5G infrastructure. So there classically would have been a small external FPGA next to an ASIC, and then you can, by embedding them in, you're effectively driving down the form factor, the cost, and the power. So there's millions of units that are currently deployed in 5G infrastructure that include embedded FPGA. The other application areas that we see are where you benefit from having that tight integration of the FPGA fabric in with the rest of the functionality. So that would be something like high frequency trading. The volumes are obviously much lower in that case, but then where you're getting the benefit is, for even just a few nanoseconds of improvement, that can have a significant impact to the arbitrage firms. And then the final application area I wanted to give was, again, another relatively low volume one, but in military applications. If you think there's classically, military subcontractors have used a lot of FPGAs. Increasingly for particularly power constraints, they're being driven towards an ASIC. But what they would like to be able to do is to have multiple different personalities supported in the same ASIC. And so you could do that with a small region of embedded FPGA that's integrated in with everything else.
Okay, thank you. That's very helpful. And I think this is the first time I've heard Achronix mention custom FPGAs. So is that kind of a new point on that continuum between embedded FPGA and your discrete Speedster products?
Yeah, I think the continuum word is exactly the right one, Bob. That you've got those two endpoints that I talked about, and you've got the lowest possible cost with an ASIC. Adding an embedded FPGA increases the flexibility and increases the die area somewhat. And then a custom FPGA is just somewhere else on that. It isn't really a different product for us. It's still the same FPGA fabric, but it's just, I guess, a new deployment of that same product where someone can come in, they can design exactly the FPGA they want, just the interfaces they want and nothing that they don't. And then from that point of view, they've got a product that's very optimized for their specific end application. Might have some hard IP in there as well for, let's say, crypto or some compression functions if you're doing a networking application. So no difference for us from a hardware or a software point of view, but effectively a new product class that enables some really interesting new usage models there.
Okay, and then I see there's a kind of a related audience question here, which is, do you provide bare die of Speedster 7T for custom chiplet packaging?
We do, yes. So that's one usage model that we entertain. I think the FPGA industry as a whole, there's some really interesting work that Xilinx has done there with multiple chiplets, and similarly from an Intel point of view. I think that having a healthy ecosystem there is great, and so having standardized interfaces. Anyone who's interested in that, I would encourage them to look at what ODSA are doing within OCP. And we support that in two different ways. We can either deploy our standard Speedster products as bare die, but people can also create their own die with our FPGA fabric, and then they could deploy them. The latter case is more efficient. It removes all of the overhead of the unwanted stuff that isn't necessarily required for a specific application.
Okay, thanks. And we've got an audience question regarding automotive applications. And I think the question is what challenges there are in terms of meeting safety standards when you add embedded FPGA to an SoC.
That's an excellent question that I'm unfortunately not going to have time to do a great deal of justice to the answer with that. Obviously, looking at ISO 26262 qualification for the final product is the key here. So in effect, what we're doing is the FPGA fabric itself isn't ISO 26262 qualified. The end product has to be. So then there's a number of aspects that need to be supported overall from a product perspective. And so we as the IP provider provide those deliverables to the end integrator, and then they get the qualification in that case. So it's a little bit different from what we would do with our standard product to get that ISO qualified, for example.
Okay, great, thanks. Okay, and then I guess I'm going to ask you from a strategy standpoint. I think Achronix started off doing discrete FPGAs and then jumped into the embedded FPGA space. You mentioned eating your own dog food. I think there was some feeling that without doing the discrete devices, you have sort of an incomplete, I guess, tool set. And so where do you see that going forward? What's the motivation for continuing to do discrete devices where you're competing with the likes of, Intel and Xilinx?
Yeah, it's, I think the two are very synergistic together. Achronix is a relatively small company. There's about 200 of us, and we're kind of punching above our weight with competing with the big guys. We do that by taking the whole FPGA market and bifurcating it into two. The high performance, bigger devices that are better deployed discrete. That's what we provide with our discrete devices. The smaller, more embedded applications, that's tough to address without a lot of hard IP. And generally, we see that customers do a better solution building their own IP. So in that case, that's where we provide the embedded FPGA. The two are incredibly synergistic. You can start your design in the Speedster discrete device and then take that through to embedded FPGA as well. So I can't see us changing our strategy. It makes sense for us. It's a little bit disruptive in that Xilinx and Intel are obviously not providing embedded FPGA primarily because of business model, I assume. But it's good because it kind of disrupts the market a little bit and allows broader FPGA deployment, which in the end, I think is better for everybody.